It started.
Good evening, everyone. On behalf of the organizing committee, I would like to welcome you all to session 7 of ATAL FDP, building the next wave of Indian startups with advanced computing technologies. It is my absolute honor and privilege to serve as the moderator of this session. The topic of today's session is quantum computing, a game changer for Indian startups. Nowadays, quantum computing is a buzzword. It has the ability to solve complex problems at unprecedented speeds and is poised to revolutionize industries ranging from healthcare, finance to logistics, and artificial intelligence. It gives Indian startups a competitive edge on the global stage by opening up exciting opportunities to tackle previously unsolvable challenges. As we start this transformative journey of innovative technology and professional development, I am pleased to present an iconic figure who will inspire and illuminate us with his extensive knowledge and insights. Our esteemed chief guest for this session is Dr. Amlan Chakrabarti, a professor and the director of the A.K. Chaudhary School of Information Technology at the University of Calcutta and a visiting professor at Triple IT Delhi. He is also the CEO of the International Center of Excellence for Data Science, Artificial Intelligence, and Futuristic Technologies, a prestigious initiative by the Department of Higher Education, Government of West Bengal. He was this university's Faculty of Engineering and Technology Dean from 2016 to 2019. He completed his MTech from the University of Kolkata in the year 2001 and did his PhD from the same university in association with ISI Kolkata in the year 2010. He was a postdoctoral fellow at the School of Engineering, Princeton University, USA during 2011-12. He has 20 plus years of experience in engineering, education, and research. He received many prestigious awards and fellowships, like the DST Boys Cast Fellowship Award in Engineering Science in the year 2011, Indian National Science Academy INSA Visiting Faculty Fellowship 2014, JSPS Invitation Research Award 2016, Erasmus Mundus Leaders Award 2017, Shiksha Ratna Award by the Department of Higher Education Government of West Bengal 2018, and IBM Quantum Researcher Access Award in 2021. He also received Hamid Visiting Professorship from the University of Cambridge, UK 2018. He has received multiple project grants in the area of embedding system design, VLSI design, quantum computing, computer vision, cybersecurity, and IoT from funding agencies like DST, METI, DRDO, DAE, the Ministry of Social Empowerment, UGC, TCS, Intel India, etc. He has also served in various capacities at various higher education organizations, both at the national and international levels. He has published around 160 plus research papers in referred journals and conferences, 4 patents, and 1 copyright. He has graduated 16 PhD students to date. He is an associate editor of the Elsevier Journal of Computers and Electrical Engineering, series editor of the Springer Transaction on Computer Systems and Networks, and guest editor of the Springer Journal of Applied Sciences. He is a senior member of IEEE and ACM, distinguished visitor of IEEE Computer Society, distinguished speaker of ACM 2018 to 20, vice chair of IEEE CADA India chapter, and vice president of Data Science Society. His area of research are machine learning, computer vision, reconfigurable computing, cyber physical system, VLSI CAD, and quantum computing. As we explore this game-changing technology today, our esteemed chief guest will guide us through its potential and its implications for innovation and entrepreneurship in India. We are incredibly fortunate to have such a visionary and dynamic personality with us today. Dr. Amlan Chakrabarti's expertise and experience will undoubtedly inspire us and us to explore new perspectives and refine our skills as educators and researchers. Now, I would like to request that Dr. Chakrabarti share his insights and invaluable knowledge with us. Over to you, sir.
Okay, so Professor Chakrabarti, you just you need to forgive me for a second. I think
Sure.
Saurabh, like Professor Saurabh Ghosh has missed a point. His very recent achievement at VLSID, where he and his team won the Best Tutorial Award. And we are fortunate enough to have him. He's not only like my friend, but he is our guide too, for not only me, for many of us. Since last, I think 2002, from his IIIT days, I know him. Anytime, 24 hours, whenever we have requested him for any sort of academic support, he's the first person to extend his hand. So our sincere thanks and gratitude to you, Professor Chakraborty, for your time. I know you are extremely busy. You have reached today morning, I think, from Bangalore. And then, although it's a very hectic schedule, but all of us, we are eagerly looking forward to your session. So thank you. Over to you.
Yeah, thank you, Professor Dhrubashish, and thanks to Saurabh. I think Saurabh was our student in radio physics, right, Saurabh?
No, sir. I'm a student MTech.
Oh, okay.
Sir, I'm
Okay.
Subroto, sir. I'm from
Okay,
radio.
Shubhata was the student. Okay, I got it.
Yes,
I got
sir.
it. Yeah.
Yes,
So
sir.
I can see his face. It looks so good to.
Sir, I basically started then sort of take the session.
Yes. You started this. So thanks for inviting. Yeah. Professor Dhrubashish is actually in VLSID. Actually, as you know, VLSID that means is one of my passion. Okay, I started this when I was doing PhD at ISI in 2005, and it is now in my blood, VLSID. We organized it in Kolkata also last year, 2024, where I was the program chair, right? And this year, that means I had to give 2 tutorial lectures, which is very very uncommon in that sense in a VLSID, because in a VLSID we have speakers from all across the world and basically industry also, but they were successfully given me the 2 tutorials to talk, right? And one of the tutorials got selected for the best paper award, and thanks for recognizing that. Yeah, that means, and in quantum computing also, it's good that your institute has started quantum computing as one of the mainstream process, because as you know, the National Quantum Mission has started. Okay, and I am the part of the technical expert committee for the quantum algorithm and applications. And though the quantum hardware hubs are already being declared, quantum algorithm application has recently been formed, I think, for the past 1 month. And we around 10 to I think around 15 scientists all over India, okay, are a part of the expert committee for quantum algorithm and applications. And I hope that then once the charter is drawn, what are the things we need to do in quantum algorithm application? We are discussing. Once the charter is drawn, I think more and more researchers will join this quantum algorithm and application research of the country of India. Right. Okay. Before starting this, as I know that this is just to motivate the industry, as well as the entrepreneurs, as well as researchers who will contribute to the product. Actually, in the National Quantum Mission, okay, I'm connected to National Quantum Mission since its inception. Okay, so the focus of Government of India, and especially the Department of Science and Technology, which heads the which is the parent organization which is running the mission. Okay, the motivation is obviously to develop indigenous technologies for quantum. Okay, it has basically basically it has 3 verticals. Okay, sorry, 4 verticals. One is quantum computing, which means the quantum computing hardware. Okay, so the quantum computing hardware, as well as the algorithms and software, the compilers on that. Okay, second part is quantum sensing. Okay, quantum sensing is also very important, because this quantum sensing means that is, I was in DRDO lab in 4th of this month, right? In DRDO lab Pune, which is a very small lab in terms of DRDO, but it is doing a lot of good work in quantum. So quantum sensing means many of the weak fields, okay, weak fields or weak signals which are there, right? We cannot detect with our sensors, which are basically classical sensors, which actually takes a good amount of signal power, a good amount of okay, field power to detect. Okay, quantum sensing is some sort of sensing by which you can detect very small fluctuations in the environment. Okay, right? And I saw an instrument in DRDO, which is basically a rubidium vapor sensor, which actually is excited by a laser pulse, right? And slightest change in the electrical or magnetic field in the area, when the rubidium vapor will change its phase, and that will generate a change in the phase of the laser output, and that will detect that there is something extra signal is available. So this is used for minings and other things. The other vertical is obviously quantum communication, which we already know is very. That means I have been to C. Delhi, right? And C. Delhi has already developed a quantum key distribution system or hardware. They are also working with post-quantum cryptography. Okay, right? These are also, that means, and they are very eager to collaborate with the various industries to take their technology and to generate. And also there are a lot of okay, QKD devices are available now in the national level and international level. That is, I work with HCL Technologies for developing the quantum random number generation. So these are very good thing. And the last part is quantum material. So these are the four verticals: quantum computing, quantum sensing, quantum communication, and quantum materials, which will drive the national quantum mission. Though, as I said, I'm not expert of all this quantum, because these are each one of them a specialized domain. I mostly work on the quantum computing in terms of quantum compiler and quantum algorithms, and I have started a new group in my research team, which is quantum communication, and we are collaborating with CDOT and CDAC Bangalore for these activities. Okay, so on this overview of this quantum computing, I will start and try to motivate you, okay, about the things we can do, especially okay, especially in terms of okay, in terms of quantum. That means to utilize this quantum machine, that utilize this quantum giant, okay, right, and try to come up with some sort of business solutions. What are the business solutions available? I will not say that our group have developed that business solution, but a lot of things our group has developed, which are now in the process of getting very good traction from the industry. Okay, so I hope my slide is visible to all of you. Professor Dhrubashish, is it visible?
Yes.
Okay. Okay. The race to quantum advantage, I said, because why we are here, because we want to generate the advantage in this particular quantum applications development or quantum hardware development, right? And what is this advantage? I will try to brief it in a few slides, and then I will go into the solutions and the business opportunities, okay, for the startups, for the entrepreneurs, what we can have. Okay. So let's see some of the interesting. So obviously, you know that in the quantum we have a lot of okay, news. Some news are really been meant to real, and some news are people can consider as a okay, that means as a sort of very much exaggerated might be, but these news are there. Okay, so quantum computing has a potential to disrupt the financial services profound in the longer term. Because why? Because this financial services runs a lot of optimization algorithms. If you see the use of optimization algorithms, right, the financial services are the best. Okay, there we have to do and the fine, and the real-time predictions. Okay, so this real-time predictions in financial market requires lot of optimization techniques and lot of that means super fast search techniques. Okay, so quantum computation has a very good that means that very good stake, right, in executing okay, this search algorithms. Okay, due to its inherent nature of actually generating a very large data space, okay, using a very few qubits. Okay, and obviously 40% of large companies, it's not 40%, it's almost now 70 to 80% of all the big players. Okay, you tell me, you name me what are the big players in computing. Okay, Google, Google, Microsoft, Nvidia, TCS, IBM, Fujitsu, it's Infosys, HCL Technologies, McKinsey, whatever that means you tell me, right? You will see that every big infrastructure company and every big services company, every big development companies, right? Qualcomm, okay, all of them have their quantum, they are in the domain of quantum ready. Right, so so you can ask me a question that, sir, why don't we see the quantum business applications in that way? So quantum business applications still will require a little bit of time because the true quantum gain will be happening when we have a true quantum hardware which can support large computing, right? And there is still some limitations to that due to the technology development. Okay, though we are almost squeezing 100 plus qubits now. If you see IBM quantum machines, it has already surpassed 100 qubits, right? And the focus is by 2025 end, it will come up with something around 1,000 qubits, and maybe by 2030 it will be coming around 10,000 plus qubits. So now all the companies are now making their quantum readiness, and now preparing the small PQs, small use cases and small proof of concept to try to find out that what are the real problems in that domain which can be well solved by quantum computer, and what is the investment they have to make in quantum computing, so that they can they don't miss the bus. Okay, so you will see that the increase in the investment in the quantum hardware and quantum applications have increased a lot. Okay. Now, now there are some of the very interesting problem, as I said, that the generating, that means solving the optimization problems. So the optimization problems are basically, what is an optimization problem? Can I ask questions to the audience, or can I make a little bit interactive? Professor Dubashish here.
Yes.
Because I'm not getting physical, so I'm trying to. Okay, so that means, so can anyone tell that what is
Professor Das, if we can, Professor Saurabh Das, if we can make all the attendees there, they can unmute themselves. So
yeah, so just maybe one of you can tell me that what do you mean by an optimization problem? That is in a very simple sense. I don't want to go into the mathematical part, but if you try to that will give a very brief explanation of what is an optimization problem, if anyone wishes to volunteer, right? And then very easy for me to understand that, make you understand why quantum computing and optimization is so closely connected. Okay. Yeah. So can you tell me what is an optimization problem? So optimization problem means either you minimize or maximize a function. Okay. That means you try to find out the parameters for which a function. So suppose there is a function which has 5 parameters, 8 parameters, 10 parameters, 20 parameters. So which means that it is a 2 to the power 20 dimensional space. Okay, right? What we can have. Okay. So these space, once I define a parametric space, I should find a point in the parametric space which will mean a particular choice of the parameter, choice of the values for the given parameters, right, and that particular point or that particular choice of the parametric values will actually define the lowest point in my space. Okay, if one axis is cost, that will define the lowest point in my space or the highest point in my space, which means that either I'm going for the lowest cost or I'm going for the highest cost if the z dimension is the cost. Okay, so we know the convex curve is that is the bottom of the convex curve is normally the way we tell that a function is minimal. Okay, so So essentially, an optimization problem is a search problem, which means that I need to find the values of the parameters which either minimizes or maximizes the function, right? And for that, we have to actually run an oracle. So if I do exhaustive search, okay, we will run through each of the possible values the parameters can have, right? And try to compare that whether this is the better than the previous or this is the worse than the previous. Accordingly, we actually move in the space. Okay, and that is called a grid search or whatever search technique you try to adapt. Okay. Okay, now in the quantum computing, okay, and in the classical, you can do one step up or one step down in each computing iteration. Okay, right? And to do that one step up or one step down, you have to look into all the parameters, okay, all the parametric combinations, okay, one by one, right? In the quantum computing, due to superposition, you can actually look into all the parametric combinations at one shot, right? Right, and then you can that is make a oracle such that it responds to the least responds differently to the parametric choice, which gives you the least value or maximum value, depending on whether you're maximizing or minimizing the function. And then there are some techniques to sample out that particular result out of all possible results, which incorporates a little bit cost. Okay, compare. Okay, so the cost in the case of the cost in optimization in case of a quantum is not in the searching. Searching can be done over one time. The cost in the quantum computation is basically the cost in the sampling, means out of the all probable outcomes, right? You have to choose the outcome which is different, okay, which shows a mark different from the other samples in the distribution, right? And how you get out that particular sample out of the distribution, that is obviously the cost in the quantum algorithms. Okay, so I'll come to that part later, but let us see the problems. So the problems of the logistic problems. So if we look into the problems which are solved in the business, right? Logistic problems are huge problems, right? The transportation problems, the freight management problems in the railways, which we are also working a bit, okay, with the railways, okay, right, and the delivery, the air route, okay, the refilling of these aeroplanes on their route, scheduling of the refilling of the okay, that means of the aeroplanes when they are going for long distances, multi-hop airports. Okay, these are all actually the logistic problems. Okay, okay, which requires optimization. Okay, there are weather studies, traffic management. Okay, okay, road constructions, signals, right? Drug design. Okay, so all these problems are actually a sort of real-time problems, and you have to find an optimal route. Okay, so so these are some of the very important problem which actually are being taken care as a very high cost problems and very high impact problems in terms of business. Okay, right, and there people have found that quantum computing can take a great role. Okay, why? I will come now. Okay, so why quantum computing is different from classical computing, and why quantum computing can actually act as a better, can actually execute a search and obviously an optimization problem better than a classical computing will be very clear to us within a few for the next few minutes. Okay, so what I show in the left is a classical computation, right, which all of us know here, right? Classical computation is the computation by which we represent the data in terms of bits. Okay, right, and this bits, if you look into the state space of the bit, means what is state space of any okay, variable or a system? It means that the possible values in which the state of the system can belong to. Okay, so if you are looking as a single bit classical data, right? The single bit classical data state space is either it can exist in the value 0 or it can exist in the value 1. So it's called the valid states of a single bit of classical data. Okay, Now, if we look into the quantum part of it, now if we look into, hey, if I just get into the quantum system, okay, what will be this simplest data representation in quantum? So in quantum, okay, the bit is represented or said as a qubit, okay, and the state space of qubit is much more than a classical. Why? Because a qubit can obviously exist in two extreme states, which are 0 and 1, which is equivalent to classical 1 and 0. Only in terms of the representing the states, you can see that there's representation in terms of Kate notation of 1 and 0 when I go to the quantum computation part, because you see that 1 and 0 are represented by two different, by Kate notation, that is a straight and the angular brace, okay? And these 1 and 0 are the two extreme states of the quantum mechanical system, okay, which can be a spin system. Quantum mechanical system can be different types, right, depending on the technology. So quantum mechanical system, okay, which presents a qubit, can be a spin-based quantum system where spin up can be 1 and spin down can be 0. It can be a polarization of the photon. It can be a direction of the current flow, across a circuit. So all these are possible quantum, physical quantum states of a qubit. Okay, but let us try to leave that, because that we are not will not get into that. That is the part of quantum technology. So okay, let's come back to the quantum computing once again. So what I said, right? I once again repeat, the state space of a qubit, which is a single qubit quantum system, is much more than the state space of a classical, because a classical bit can only exist in 0 and 1. Vis-a-vis, a qubit can obviously exist in 0 and 1, the two extreme states, but it can exist in a superposition of 0 and 1, because if we go to the vector, any orientation of the vector between the extreme up and extreme down are the all possible states. And this vector can have infinite number of states, actually, okay, because the mathematically represented as C1, 0 and C2, 1, where C1 is the probability of getting C1 square is the probability of getting measured 0, and C2 square is the probability of getting measured as 1. And this C1 and C2 can ideally take infinite number of values, provided the constraint is root over C1 square plus C2 square should always be 1. So maintaining the constraint that root over C1 square plus C2 square equals to 1, you can have all the possible different values of C1 and C2, and each will be a different psi. Each will be a different quantum state. So what it means is that, again, I come back to reiterate that a single qubit can generate much more states in its state space compared to the single bit classical system, okay? And that is one of the power of quantum computer, okay? Okay, now we have to use that power, and this power is called superposition, power of superposition, and we have to use this power of superposition to actually make certain implementations or certain applications, okay, which are not possible in the classical domain, okay? And now this when we go to from a single qubit smallest quantum system to an n qubit system, what we actually generate, we generate 2 to the power n possible states for an n qubit system. Okay, so 2 to the power n possible states using an n qubit quantum system, it means that you have computationally, you have an exponential power of actually representing the data, okay, using your qubit resource. So in the case of classical, the bit resource and the amount of computation you can do is linear, which means that if you are doing a 16-bit register, if you are storing 16-bit, right, you can do 16-bit operations. If you are storing 32-bit in your memory, in your registers, in your data paths, you can do 32-bit of operations. But in the case of classical, okay, that means in the case of quantum, If you are storing 4 qubits, you can do an operation over 16 states. If you are storing 5 qubits, you can operate on 32 states. If you are working on 6 qubits, you can operate on 64 states. So it means that the amount of resource you give and the amount of computational data space you create, or the operational space you create, is basically exponential, okay, to the resource. And that is why it's called this. And this space, in terms of the quantum mechanical phenomenon, is called the Hilbert space. And when we try to update this quantum state, it is known as a transformation on the quantum state space, which is called a Hilbert. And this quantum state space, okay, I repeat, this quantum state space is called a Hilbert space, right? And there are certain specific rules to update the quantum state space. So suppose I want to change from psi to psi dash, which means that I'm doing an update in the quantum state space, or we can say an update in the Hilbert space. It means that there are certain transformation rules we have to follow, and these transformation rules are basically unitary transforms which can change this psi to psi dash, and these are logically called as quantum gate operations. Okay. Okay, I'm trying to squeeze a little bit due to the time, but these are called the quantum gate operations. Okay, right, and these quantum gate operations transforms the qubit system, okay, from one particular state representation or set of or a state psi to a state psi dash. Okay. Okay, so we have already seen the power of superposition. Okay, so as I said, that if a 3 qubit, that means now a little bit change. I go in the right side, I go the classical one, and the left side the quantum one. So in the right side, if I show the classical one, if I have a 3-bit register, I can only store one particular string having 3 bits. So it is any one string from 00 to 11. So for example, I have stored here 110 in the classical system, but in the case of quantum, each of the bit can be either 1 or 0. Okay, so we can have all possible combinations from 000 to 111, because if we consider every qubit can be either 1 or either 0, depending on as every qubit can be superposition, then the probability of each of the strings means 00 to 111 exists, right? And that probability exists means that, hey, there is some probability of getting this register measured at 000, some probability getting this measured as 001, and this way some probability of this register getting measured as 111. Now these probabilities can all be equal if we do certain operations. And these probabilities can be very different. So I can make certain quantum transformations on the 3-qubit register by which I can make the probability of getting measured maybe 011 is quite high than all other 3-qubit states, right? And to do that, I require to do some gate operations on starting from the initial all 000 qubit values, right? And that is what is a quantum algorithm. So how from a one distribution of the qubit state space, you generate another distribution of the qubit state space. Okay, that is called the quantum transformation of the quantum gate operations, or a sequence of operations called quantum circuits. Okay, so what I again come that actually you can have the entire parametric state space, okay, represented if we have if we have capital N amount of data, okay, where which can move. You can use a qubit system which is of log n size, log n resource, and you can represent the entire data. Okay. Oh, now the second part of it. Okay. Second part of the quantum computation is entanglement. Okay. In the classical computing, entanglement is not there, right? Entanglement means that if 2 qubits are entangled, okay, if I am operating on one qubit, on a part of the entangled qubit, okay, the other part of the entangled qubit will also come into play, will also have its change, right? So if you can try to imagine that you're trying to work on a function, right? right? And the function is of a that means is working over a large number of values, right? And if we represent the different values with different values with the qubits, then you can actually, and if they're entangled, you can actually generate the all, that means the function is operated on all the possible values of the function at one particular shot, if you can make this entangled qubit states. And these are very well used in communication also. In the case of communication, that means that if you are doing an operation on an entangled qubit on one particular part, the other particular part you don't need to measure, right? You automatically know what will happen, because one part of the entanglement qubit is so closely correlated with the other part that if you observe one part of the entangled qubit, the other part is already known, which is the sort of communication happening between the A and B. And this you can do with the multiple qubits which are entanglement. Though having said so, mathematically the things can be very well explained, but when we come to the physical state of the system, in order to achieve this, you need a lot of things to be done. So suppose take a business use case. So calculating the possible returns of correlated stocks. So if there are correlated stocks, right? If you have to evaluate a function, right? You have to do the function on that means on each of these data independently, each of the records independently. But using a quantum system, you can generate an entangled representation of all these correlated stocks, and you can only estimate, only run the estimation on one particular stock data, right? And if they're entangled with the other data are entangled to this, automatically the operation of this particular function will be evaluated on all other stock data. So this is a particular example, but if you can frame the problems in this particular way, the quantum entanglement can obviously help you. The third part is obviously what is really something which is scaring us. The number crunching problem. Number crunching problem. One of the most spoken about number crunching problem is generating the prime factors of a large number. For example, as I show here, factor a 300-digit number. The best computer, the best algorithms take 10 to the power 24 steps. On a computer working at a terahertz speed, you know that the terahertz speed is not there in a single clock computer. Probably you can have a parallel computer of a large size, and you can still make a pseudo this type of speed. Right? And this requires almost 150,000 years to do it. Right? And that is a tough problem. So the problem, again, I repeat, is suppose we have 463 it's only a 4-digit number. To find the prime factors of 4633 is 41,113. You require to apply, right? And this is the core of the RSA algorithm. Because the RSA algorithm incorporates the keys, the two keys, public key and private key, which depends on the prime factoring. And in the classical case, this is RSA algorithm is good because there's possibly we will not able to find the prime factors. Nobody can able to by brute force probably find the prime factors of a number of 300 digit and try to crack the communication which is happening. But let's see that what happens in a quantum computer. So in a quantum computer, it becomes 10 to the power 10 steps, and in a quantum computer, probability will reduce to an order of seconds. And that is why you tell that, right? And this algorithm was proposed and explained by Peter Shor of IBM, which is called a phenomenon Shor's factoring algorithm in quantum computing. Right? And this algorithm is really giving a real threat to our crypto systems. Right? And many of the and so the algorithms what we are now now coming up with the standards in crypto systems are called PQC, which means that post-quantum cryptography algorithm, which means that these algorithms are proven not to get jeopardized or cracked by the computing by the quantum computing techniques. So now, if you look into the latest standards of NIST, you will see that they are proposing the PQC standards of cryptography. Okay, so that so the quantum computer. So when you try to establish a PQC, you have to show that this algorithm is not vulnerable. Okay, through quantum attacks. Okay, so that is also one of the very important thing in quantum systems. Okay. Okay, now if we try to look into that, hey, that means being an algorithm or being a developer, and I try to build a quantum application, how should I proceed? Okay, obviously the first part is problem definition, which is there in the classical too. Okay, the second part is the quantum algorithm. Remember that when you are telling a quantum algorithm, it means that you are using the quantum properties like entanglement, superposition, and interference and measurement to actually use it in the algorithm, right? And if you can use those in the algorithm, probably you have come up with a quantum algorithm. So quantum algorithm is only will be taken care as a quantum algorithm if you have sufficiently proved that the use of this particular phenomenon in the algorithm makes the algorithm better and can show the quantum supremacy. So once you develop the quantum algorithm, which is better, right, you have to convert the quantum algorithm to a sequence of quantum operations, which are called quantum circuit, right? And this is still in the functional form. So quantum circuit is still the functional form of the quantum operations. But actually that means you can now go into two ways. You can try to simulate this and try to verify this, or you can try to test this on a real quantum processor, which is called QPU. So you see so for that, you require something called quantum compiler. So what the quantum compiler will do, quantum compiler in one way will try to take your quantum get description. If you are targeting a quantum processor, it will take the quantum description, the sequence of quantum gates and operations on the qubits, the initialization of qubits, into a sequence of control operations on the real qubit hardware, which will generate these qubit transformations, initialize the qubit with the data what you show in the quantum quantum circuit actually, and try to apply measurement and give you back the measurement results. And from the measurement results, probably you can verify whether you have correctly executed the algorithm on the quantum hardware or not. If you are going to a quantum simulator, you have to understand the simulator is working either on a Python or on a C++, basically a C++ backend. Okay, so you have to convert the high-level quantum circuit description to a C++, and might be it will go further to a particular processor or a GPU to hit. Okay, so that particular level of micro instruction is to be generated so that it can be simulated by a multi-core machine or a multi-core GPU machine. Okay, so the compiler will be generating those micro instructions targeting a specific classical hardware. But you have to understand that when you run a quantum algorithm on a quantum simulator, it's running on a classical system. You will not able to blow it up in a very large dimension because the simulator will, the computing resources will be less because you are doing a classical using simulate quantum system using classical. Vis-a-vis, if you are using a quantum processor, you will actually get a supremacy. But again, there is a restriction at the present scenario because the present scenario quantum processors are not very high qubits and they are still very noisy. So it's called NISQ, noisy intermediate quantum computer. So probably you cannot verify a very large algorithm or a very, very large problem in the present quantum processor. Right? You can go with a very small version of the problem. Vis-a-vis, you can go to the quantum simulator and you can simulate a larger problem. But again, the issue is that you need to have a lot of resources. And secondly, that means it is running on a classical hardware. So you will actually not get the supremacy, but you will only can able to verify that. Okay. So, so obviously there are, if we look into the entire set of the okay, of the applications what you can run in the quantum domain, or the solutions you can quantum domain, right? You first of all, you can go into the choice, right? So problem domain, maybe optimization, simulation, machine learning, cryptography. Problem class, right? Okay, what are the exact algorithmic class, okay, you will use to solve these problems? It will be knapsack, it will be traveling salesman, it will be satisfiability, computational fluid dynamics. These are the different problem classes. Okay, because if you can map the problem class, then probably you can use certain existing algorithms or models in this problem class to solve the problem. So first of all, you understand the problem domain, then you try to understand the problem class, right? And then you try to see what are the exact mathematical models, mathematical techniques you need to do to actually generate the solution in this problem class. And then comes the quantum algorithm, right, which will be a quantum version, okay, of this particular models or functions, okay. And then it comes to the which quantum architecture or which quantum machine you want to implement that or execute that. So this is the entire. So those who wants to develop a quantum ecosystem, or those who wants to develop the quantum business use cases, they have to go into this, and they have to see that whether that means that how they will approach the problem, and they will actually come up with a solution which is implementable. Okay, so you have a business impact. It should be generalized. That means you should have an access to the quantum resource, and then you find the technical feasibility there. Okay, right. And this is a scenario, and this is a scenario which is, sorry, just. And this is a scenario which tells you that, hey, what are the, okay, this is a consortium called QTAC, okay, which is a Quantum Technology and Application Consortium. This is all the top companies in quantum, okay, they are working on this particular technology, okay, this particular consortium, okay. Okay, IBM, NVIDIA, Qualcomm, Pricewaterhouse, whatever you say, okay. Right, and they have identified that, hey, these are the domains: material science, engineering and design, production logistics, post-quantum era security, industries where it can target. What are the business impact? What are the specific problems we have to solve in the quantum domain? Okay, simulation, cryptography, optimization, machine learning. So this is a very well drafted report from QTAC. Anybody can search it in the public domain. It's a white paper, okay, from which I have taken the diagram. The rest white paper looks pretty good. So those who wants to generate a business idea from the quantum, and what are the directions, and what are the depending on the strength okay, of the quantum team, what are the direction he or she has to take, it can be taken ahead on this. Okay. Okay. So how much time I have? Okay, anyone from the organizers? I will cut short my lecture accordingly. If you can tell me how much time I have. Anyone from the organizers? 5 minutes, 10 minutes, 20 minutes?
It is up to 7:20.
Oh, it's up to 7:20. Oh, okay. So I have at least 15 minutes. 15 minutes to go, right? Okay, fine. Okay. So yeah, so what I show here is that which are very that I'm not getting into this into great details, but this is a business. This is a particular very good contribution from our group, which was the probably the first quantum ant colony optimization okay, the algorithm which came up, right, and developed by our group. Okay. Okay, so as you can see that, okay, there is a MNDAS. Okay, so the authors are Mrityunjoy, who is my PhD student, and he is submitting thesis. He is a principal quantum engineer of ACL Technologies. Nivedita is also my PhD student, but she's now with PwC. Devdeep is my PhD student also currently, but he has worked with quantum initially, but now he is working in different problem space. And myself is Amlan Chakrabarti. Okay, right. And the last one, S. Okay, that means I don't know whether you know this. This S is basically of our okay, phenomenal professor, Professor Shubhangshu Bandyopadhyay, okay, who was there with us, okay, when we started this problem in 2019, and we finished this problem in 2020, and we got it published in 2021. But as you know, that we are very unfortunate that 2021 in the February, Professor Shubhangshu Bandyopadhyay, that means left all of us, okay, right, and gone to the heavenly space, and so that's why we give the name of the problem MNDS, because Professor Shubhangshu Bandyopadhyay was a part of the thought process of this algorithm. Okay, right. And why this algorithm is important as one of the milestone in Indian quantum computing, which is being considered, because this algorithm fetched us the IBM Quantum Researchers Access Award, which we won in 2021. And this was the first Indian research group getting this IBM Quantum Researchers Access Award for research. Though there are a couple of institutions like IIT Chennai and ISI Calcutta, they also got this Researchers Access Award, but that was basically for training. Okay, but we are the first group in India who received this this Access Award for research. Okay, so that was the contribution of this algorithm in our Indian perspective. Okay, there are a couple of things which the business community and the people who wants to become entrepreneur can either take this ahead or can plan something new. This is our journey. What we say, this is something very, as you know, that we are basically the quantum computation group. So we developed a quantum compiler called QRZone, which is one of the type of compiler where we can distribute a distributed quantum compilation, which means the parallel execution. Because as you know that the quantum computation is heavy. Why? Because when you go into I said that the gate matrices, which define the transformation on the qubit space, they are unitary matrix. And unitary matrix dimensions are 2 to the power n plus 2 to the power n, where n is the number of qubits. So more and more we increase the size of the qubits, okay, the transformation matrices size becomes exponential, because it's for 2 qubits it is 4 cross 4, for 3 qubits is 8 cross 8, for 4 qubits is 16 cross 16. Okay, so this way as we increase the number of qubits, okay, the size of the matrices of the transformations of the qubits to evaluate the qubits or to simulate the qubits, they exponentially explodes. Okay, they exponentially explodes, and that exponential explosion requires a lot of resources, and probably if you can have a distributed algorithm, probably you can have a better thing. This was a work what we did and published in I think in 2021, right? And this student who worked with me as an intern, Turbasu, who is now a master's and a PhD student in Virginia Tech, who moved from my lab and joined Virginia Tech, right? That means it was also a good good landmark in our that means in our activity. Okay. Then this is also one of the landmarks which as Nivedita has done, and this paper will very soon come up in one of the good journals. So this is the first of its kind work that is where we can develop a quantum development life cycle. Like we have SDLC, software development life cycle. We have developed a particular the life cycle of quantum business development, starting from the feasibility study to the maintenance. What are the things we need to do in a quantum development process, and what are the tools we need to do? What are the cost estimation we need to do? What are the checks and bounds we need to do? What are the choices we can make in various steps of the quantum development process? We have very well iterated through our study and through our visualization and simulation. So this is also a paper which is being which will be published pretty soon, right? And this is also a very phenomenal work which has been already published now in ACM-JETC, because the error is one of the very important thing in our quantum computation in the physical hardware. So we used a machine learning technique to figure out the quantum gate and qubit feature space and try to generate a probability of the error for a given quantum circuit description, and try to find out that what is the best size of the circuit which will reduce the error, okay, which will make the error within the bound, okay. So sub-circuit generation for a given quantum circuit, and try to find the best sub-circuits for a given large quantum circuit. And this was done on the basis of error prediction on the quantum circuit feature space, okay. This is also there's some sound coming up in the back. If somebody can switch off the microphone, I think someone's microphone is getting a noise. Okay. So yeah, so this is also a phenomenal work which is a little bit advanced. You can say that that means, sir, whether we have the things now to work it out, but okay, but in research and in product development, it is always better to be advanced. So this is the first of its kind simulator in the world. Okay, I can now very strongly say this is the first of its kind simulator in the world. Okay, called QDIT, which is a collaboration between our group in University of Calcutta and Nanyang Technology University in Singapore, where we developed the first simulator called QDIT. Okay, which is a simulator which simulates the quantum. What we discussed till now is called the binary quantum, because we have said that, hey, if you have n qubit, your number of states are 2 to the power n. But there are ways by which we can make it to a ternary quantum circuit or a ternary quantum state space, where an n ternary qubit will generate 3 to the power n basis states. And ideally, it is called a QDIT, which is called a D array, binary, ternary, quaternary. And ideally, it's called a D array qubit system. So a D array qubit system will generate d to the power n spaces, okay, state spaces. And that is a very, very large space. But again, having said so, whether technologically it is possible that we can have from the binary to the D array space, this is challenging, but you will see a lot of good groups in Europe have already started working on this multi-valued quantum logic, right? And we started working multi-valued quantum logic long ago, 2012, when one of our students, Sudhendu Bikash Mondal, who is now present in the TCG Crest. Okay, I started working with me and my PhD supervisor, Professor Shushmita Shurkole, and we continued that. Right, and recently my PhD student, Dr. Amit Shah, okay, graduated from my lab and also joined ATOS, right, and now he's a postdoctoral fellow in India. He has phenomenally work done in this particular domain, and probably I'm just very hopeful, and probably we will be coming up with a very good IEEE publications, okay, that will earlier of this year, because we're almost through in this particular work, okay, in a very top level journal, okay. Okay, and what I can say apart from this, we have a startup called QRD Lab. Though it is started by my students, right? I am basically mentoring that due to the students coming and going and joining new offices. Obviously, this is getting a little bit off support, you can say. But any entrepreneur here, anyone here wants to rejuvenate the QRD Lab, which has already got a very good name. It started with training a lot of the researchers from IITs and NITs, right, to the support of IBM, right, and then we also developed some technology for some of the companies in Middle East. But obviously that means if some entrepreneurs is willing to actually join or converge in QRD Lab, we will be very happy. Apart from that, we have the technology partners like HCL Tech. Okay, that means who works with our Infosys also, we discussed something. And there are some companies like NVIDIA, Infosys, TCS, where we are discussing, and some of the things we work together on this, okay? right? And we have a lot of universities like University of Buffalo, Nanyang University, ISI Kolkata, and now a lot of TCG Crest also comes as technology partners for us. A lot of this data is a little bit older. Okay, maybe in the last 3 years, our lab and our group has connected to more number of international institutes and corporates, okay, through our research discussions and solutions, okay. Yeah, this is a research group. This is a current research group. That means I might not have incorporated all the names and all the teams, but okay, but these are looks good because the students who have finished PhD are well placed in the right in the industry and postdoctoral positions in the top labs of the world. And some of the researchers that was also doing fantastic in terms of postdoc, right, in terms of undergraduate research with our group. Okay, we have a lot of avenues who wants to collaborate, industry, academia, research wants to collaborate. We have the quantum CAT, quantum algorithms, quantum ML, quantum cryptography, all these verticals we do research strongly, and we collaborate with multiple as you see, collaborate and funded by multiple corporates and collaborate with multiple top universities across the world and across India. Okay, so the last thing, obviously, quantum computer. There are challenges and market barriers also, right? Right. I shown a lot of things which we have already done on quantum computing, but obviously that means at large scale, right? We need to do many more. Okay, decoherence is one of the things. Decoherence means that, okay, that means you have a qubit state and you are trying to operate it with number of quantum gates. How long you can do this? Okay, it has been seen that you cannot continue quantum operations on the qubits for a very long. It only lasts for a few order of nanoseconds. Only a few nanoseconds you can do, okay, this operation, okay. Scaling, right? Right, the technology, okay, it has grown much. When I started my PhD, number of qubits was 0. No qubits was there. Only the theoretical concept was there on which I developed the PhD thesis. And then I went to Princeton, and the qubit was a little bit coming up. Okay, when I came from Princeton back to India around 2000, I came back 2012, but 2013 or 2014, IBM first actually came up with its version of superconducting qubit quantum computer, right? And now from the 5 qubit stage, it has crossed almost 1,000 logical qubits and 100 plus physical qubits, which is obviously fascinating. Okay. Okay, the I/O control is very critical because, as you see, this is RF. RF, if you're looking for superconducting, it's RF. If you're going for optical, it's laser. If you are going for ion trap, also it's a laser and laser. So there are different types of control things are there, and readout is also not so simple. So the input and output, of the both, to the qubit system is basically a very highly technology supported controls. So you have to do that. Extreme conditions, if you are going for superconducting, cold atom, all these are going with the cryogenics temperature, so you have to have those cryogenics to be done. Measurement policies are variable, measurement policies are error, so we have to have a very good measurement policy to have the high gate fidelities of the quantum, high gate fidelities and quantum states. Okay, compliance means you have control system, you have cryogenics, you have qubit systems, you have readout mechanisms, software, operating systems. So many things are there in the quantum entire stack, from the algorithm to the hardware to the control. You need to have maintain a sort of standard and compliance to achieve everything for a particular common goal. Okay. Quantum algorithm is a difficult thing, right? If you can develop a quantum algorithm, it's a big bang, right? Whoever comes up with a quantum algorithm, new quantum algorithm, obviously he or she will be on focus. Okay, so always I will tell you, try it, but it is not the only thing you should try in research, because making a novel quantum algorithm is a hard task. Okay, most of the researchers, if you see, is using a quantum algorithm and solving a problem. Okay, but if you tell that, hey, I will try to come up with a problem like that is an algorithm like a law of Grover search, or Peter Shaw's, quantum factoring algorithm, right? Or maybe QAOA, or maybe something like that. That means it's obviously something which you have to achieve with a very hard work. Okay. And as I said that though we have developed the QDLC, which is one of its first kind of a business platform, but we have to long go in making the business development platform attractive. AKCSIT has played a good role, the IBM platform, to make a very ready to go quantum platform. NVIDIA is also trying to generate a CUDA quantum platform. That with AKCSIT is also developing a platform which is basically the to get into the technology part of the quantum, right, and to see that means to see the qubit to simulate the qubits in the physical system. They have also their own tool, right, and many of the other tools are there. But this is this set of tool chain which is very standardized in case of the VLSI design or other the HPC type of systems. Needs to be more standardized and user friendly, and more work needs to be done in this domain. So that's so for an entrepreneur, for a business investor, or for a technology developer, the challenges are important, right? The challenges are there, so you can contribute and you can come up with your solution, which can make the ecosystem better. Okay, so that's why you don't think that challenges are the bottlenecks. Okay, in technology, challenges are the opportunities, right? If you can overcome one challenge to a certain level, that means you are really taken ahead. Or if you can take more challenges in the near time, right, you will be obviously will accelerate it. Okay, so that is the positive vibe I want to give to all the researchers, entrepreneurs, the business persons from the business. Okay, to take that, hey, quantum is something which is new. Okay, which has obviously some challenges. Okay, but if you have a thought process of investing time and money, right, it can give you some gold mine, maybe in the near future. Okay, yeah. So thank you all. I hope I am within the time, and I am ready for some questions. Yeah, please go ahead.
Audience, do you have any question? You can directly ask. Please kindly raise your hand. Okay. Sir has a question.
Yeah, please go ahead. Please go ahead. Yeah.
So it's a very exceptional session as always. So my question is, look, whenever cloud computing came into existence or into the market, it has given birth of some sort of techno-driven business. Say suppose software as a service or infrastructure as a service, such kind of. In your opinion, as you are the expert in this field, do you think that if quantum computing is in place, other than solving the conventional business problems, because end of the day, business will give the money and people will be interested. So other than solving the business problems, do you think that quantum computing may give birth of some sort of other dimensions of technology-driven business?
Yeah, very good question. Very good question, Professor Dhrubashish. I will just come to first. That means I will give one answer. Which is very well connected to the cloud. So cloud you mentioned pretty. That means obviously a good point, and I didn't touch this point. Okay, that means for all of your knowledge, quantum cloud is available. So what I thought when my PhD is a quantum computer, which will just be a computer in my table, right? It is not that, right? It will not be like that because the way the complicated electronics, the cryogenics will work, you cannot make it like that. Now, if you look into the IBM version, okay, the AWS bracket, okay, Microsoft QSARC, okay, right, Penillion Quantum ML, all are quantum cloud versions, and what needs to be done is that this quantum cloud will generate the new quantum services, which will be connected. That means which will be infrastructure as a service for the people who wants to do R&D. Okay, platform as a service. Okay, that means those who wants only development. Sorry, the infrastructure as a service for who want to do research. Platform as a service for whom want to do development. And maybe you can sell your quantum offering, okay, like Amazon, okay, like HCL. HCL is now selling a service called quantum random number generator. Okay, which means that, hey, if you want to have a real random generator seed, right? And if you want that, because it didn't go into that level, the quantum states in physically are random because it cannot stay in the same state for maybe for a fraction of a second. So whenever we sample a quantum distribution, every time it will be a new distribution, right? And that is maybe a varying slightly from the previous distribution. So that itself generates a randomness, and this QRNG is now offered as a service. HCLTech offers as a service. So suppose you are a banking corporate, right? And you want a sort of seed which is perfectly random seed so that you can drive your transaction. Okay, so you connect my QRNG to a QRNG API. To your application, and this QRNG API will feed you in stream the quantum random number. Okay, so this is one of the service which is already existing. Okay, in communication, a lot of services are coming up, right? Already DRDO has established, as I said, I visited the lab. DRDO has established a very good communication with 100-kilometer in the hills in the northern part of our country. Right, and these are the applications. Right, and CDOT has said that for strategic communications, government is now going for QKD. Okay, so these are obviously the services which are very different from the classical services, right? And I hope that a lot of things will be coming up in the next few years. But it's a very good question. That's the direction where we all trying to get ahead. Yeah.
Thank you. Thank you.
Sure.
Shubham sir.
So just you have mentioned about the quantum random number generator. So as we know, in classical computer, it is not possible to generate the real random number.
Yeah, it's all pseudo-random. It's all pseudo-random.
Pseudo-random. So my question is, it is really the random numbers are generated or pseudo-random?
Yeah, really random is generated because why in the classical we cannot do? Because for the classical to make a pure random number generator, we require that was almost an infinite repetition of your LFSR. Okay, which is very difficult to do because then you require an infinite amount of storage to do that. Okay. But in quantum, the inherent nature of the quantum, because here we are capturing the states which are subatomic states of matter, right? In the subatomic states of matter itself, there are so much of oscillations. So the good point of random, so the best point of randomness is noise. So now if we can capture the noise, okay, that is the best random seed. Okay. So what happens in the quantum is that means if we just try to make the system free without any sort of external control, right? This free system will interact with so many fields will interact in that particular thing. You will always see that the states of these qubits, of this subatomic states are always changing, right? And if you can take one snapshots in time cycle, right, you will see that the snapshots doesn't repeat. Okay, right? And that is what is a true quantum. So the true quantum in the case of a quantum system is generated by a physical process. Whereas in the case of a quantum random number generated in the digital systems at present, right, are generated by an algorithm. Okay, so that algorithm cannot actually have the true random because you need to have an infinite repetition circle. And for infinite repetition circle, you need to run a finite state machine, which is very nearly impossible to do that. Yeah.
Okay. Next, Sumit has a question.
Sir, I have one more question.
Okay,
sure, please
go ahead.
Sir, regarding the power distribution, so as we know today in the machine learning and AI era, basically the testing is major challenge, and as it is a major challenge as the VLSI designer as well because of the testing power. So what about the power distribution in case of quantum circuits?
Yeah, so quantum circuits, one thing is good in quantum circuits in terms of power is that quantum circuits use less resource to do the same computation. So each resource, if needs to be power enabled, okay, then quantum circuits requires less power to compute the data compared to the classical because it requires less resource. That's the first, because it can scale up to 2 to the power n data states with n resource. Okay, the other part of actually the power is low. This is also true, but there is a little bit thing that once we, because it takes, that means the operation of the qubit actually takes almost no power. The power actually is taken by the system to cool down and to generate the readout and the control. Okay, so now people are coming with new technology, which is instead of making the lines of controls outside this particular cavity, because once we make the control lines outside the cavity, and if you are moving the control signals at a terahertz speed, right, you require good power. Okay, to move the control signal from your controller to your qubit. Okay, so now people are trying to make this controller as close as possible and as compact as possible so that they can reduce the line, right? And they can actually use it. And secondly, to run this cryogenics, which requires a power, people are trying to make a very smaller cryogenic as small possible. So ideally, quantum computer, okay, if it would have run in the same environment as classical is running, it would have taken much less power. But then to make that environment happening, right, you require a good amount of power for cryogenics and for control signals. Okay, so that's also another line of research now, which are basically from the quantum technology experts, that how to reduce the cryogenics and how to make the control signals channels much shorter. Yeah.
Yeah, thank you, sir. I'm very proud of your student as well. Thank you, sir.
Thank you.
Sumit sir, please ask.
Hello.
Yeah, hello, please go ahead. Yeah.
So we know that in quantum computing, it is prone to a lot of errors. So what is the best way we can minimize as minimum as possible?
Okay. Yeah. So the algorithmic technique of reducing error is called error correction. Okay, where we use some error encoding technique. Okay, so that each qubit we have the data, we use maybe 2 or 3 qubits more to encode that particular qubit, so that at the receiver side, when who is capturing the data, we'll look into the redundant bits and we'll look into the signature and we'll try to see whether error has happened in the specific qubit or not, which are our classical error correction techniques like CRC, like parity, like whatever you can say. The same techniques can be employed in the quantum. The only problem is that in the quantum you cannot have so many number of qubits now. Okay, because you then lose the data qubits and you use more redundant qubits to encode the error, which is obviously costly. So now, this will be the qubit. This error encoding can be done in the qubits once we reach to the era of 5,000 qubits plus, which is called the FTQC era, fault tolerant quantum computing era. Presently, we are having a qubits which is between 100 to 1,000 qubits. Okay, so 100 to 1,000 qubits are something which is basically called NISQ. So in the NISQ, the only possible is that you take the shorter version of the algorithm, don't run very long, because if you run very long, the recordance time will capture and the qubit error will be higher. Okay, so you capture small and you make we have certain work on that, which is the circuit cutting. So you try to make a large circuit cut into small fragments, and that means, and try to implement those fragments into low qubit QPUs, right? And then try to use a measurement function which will try to unify all the results and give you a final result. Okay, so those are the techniques which are used for the less qubits era. That if you see our work, the IQER, which was published in 2021 in ACM Jersey, and recently we have published a work in FRAC-QC and Elsevier Journal of Software Systems. Okay, these two work are there. A phenomenal work is also done by the group from the Rolf Dreschler's group in University of Bremen, where in one meeting I saw they are using teleportation to encode the qubit from one circuit to another circuit, and those are the things which are used. But these are the short-term effects, short-term game we are playing. But ultimately, we are hopeful that 5,000 qubit will coming in 2027 or 2028 or 2030. So once FTQC are there, then we will try the actual error encoding, and we will try to almost match the classical error corrections.
Okay. Thank you, sir.
Yeah.
Sir, I have a question.
Yeah, sure.
Recently, I am working on an IoT device. I want to extract some data from there. So can I replace the traditional sensor with the quantum sensor?
Very good. But it's still very costly and very bulky due to all the assets. So you can connect to, if you are interested, you can write a mail to me. I can connect you to the DRDO lab, right? What it is doing, the quantum sensing for magnetic signals, for magnetic fields. Okay. They have the prototype. They have a sensor which is itself the sensor. I don't have the image. The sensor is at least a 6 centimeter by 3 centimeter 3 centimeter cavity. Okay, right. In that, a laser input comes, and that means, and a photo detector is an output. Okay, but in order to control all these lasers and photo detector, you have a big what I can say, a big control hardware. Okay. So provided all this is controlled, and you can do, but if you want to do quantum sensing, the good group is in IIT Bombay. Okay, right, and Madam Kasturi. But DRDO group is also doing good. So if you want to do anything, I can connect you to DRDO, and you can see that how your IoT and quantum sensing can work. Okay, but it is doable. It is a doable experiment you can do always. Yes.
Okay. Thank you, sir. Thank you.
Sure.
Any more question from the audience? Okay. I think there is no more question. So if you have any more questions, so you can directly text in the group. I'll definitely share.
Yeah, that means you can connect with the organizers, anyone. Okay, Professor Zubashir or Professor Shourabh. Okay, they will push me the question. I will answer it offline. No issues.
Actually, it's a great pleasure as I'm attending your session. I am also your student.
Oh, so good. Yeah, you're in WBT, right?
No, sir. I'm not WBT. I'm in Shibpur. In 2009,
okay,
11.
Okay, great.
In the IT department.
In the IT department, I took lectures. I think before I went for
postdoc. System.
Yeah.
Image
processing. Yeah. Image processing. We had a paper. I think you have a very good paper which was designed by Bhargav Bhattacharya at the course, and I used to take that. Yeah. Okay, I got it. Very good.
Sir. Thank you.
Nice
sir.
to meet you.
Me too, sir.
Nice to meet you. Yeah. So has Shandip already joined here? Professor Shandip Shukla? Has he joined?
Not yet, sir.
Not yet, sir.
Okay, fine. He's also a very good senior dada of me. I just say hi from my behalf. We met, I think, 1 month ago in a verbal meeting in Kolkata. Yeah, he's also a very good prof. Yeah, very good. Thanks.
Okay. So I think there's no more question. So let me conclude this session. So I want to express my heartful gratitude to our esteemed chief guest, Dr. Amlan Chakrabarti, for sharing his deep insights and expertise. Your thought-provoking session has not only demystified the concept of quantum computing, but also highlighted its transformative potential for the Indian startup ecosystem. Quantum computing is no longer a futuristic concept, it is really knocking on our doors. Today's discussion has shown us how the cutting edge technology can empower startups to solve real world problems, innovate with agility, and redefine industry standards. So I also want to thank everyone for your interest and curiosity throughout this session, and the active participation and thoughtful question were a testament to this enthusiasm and the interest the topic has sparked. So prior to conclude this session, I invite Dr. Dhrubasi Sharkar to share a few words and officially close it. Thank you, sir.
Always like spellbound session, and you'll be happy to know, Professor Chakrabarti, that close to 170 participants across the country, where few industry professionals are also there, spreading across 60 more institutions. They are listening to you. So
very good organization, excellent organization.
And one more request to you that, like last time also, there was a plan that you will be physically visit and take the session. You could not.
Sure.
So very soon, like we'll be organizing one program, and you have to come.
Sure.
Best wishes for your ICDMI, because that is going to take place.
You are also coming.
Okay. Yes.
I know you are also coming. Thanks for coming.
Yes, I'll say yes. So I'll meet you there.
Yeah.
Thank you.
Thanks. Thank you all. Take care. Good night. Take care. Take care.
Thank
Bye.
you, sir. Thank you.
Bye. 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 Bye.
Good night. Professor Sorkar, am I audible to you? Doshi sir?
Yeah.
So, should we take a break for 2 more minutes, 2 minutes, or should we continue?
No, like as the time almost 7:26, so just
Right, sir.
I think Sitoma madam is ready.
Madam is ready.
So what we can do, we can stop the recording session right now, and you can just wait for 2-3 minutes. I'm sure Professor Shukla will join by that time.
Okay, sure. So meanwhile, it is